This chapter deals with two-dimensional motion, but before we can discuss two-dimensional motion, we need to discuss the mathematics needed for two-dimensional motion, and the mathematics needed for two-dimensional motion is vector algebra. So in this section, we're going to deal with vectors. Now, physical quantities are divided into two based on how they are represented. They're called scalars and vectors. So let's define scalars. These are quantities that can be represented by a number and a unit only. A number and a unit only. In other words, they do not have directional properties. For example, if you take length, if I say the length of something is 2 meters, that's all you need to know. You just need a number and a unit to represent it. It doesn't have directional properties. But there are other quantities called vectors that have directional properties. These physical quantities can be represented by a number, a unit, and a direction. So for these physical quantities, we need direction in addition to a number. Okay, they have magnitude and direction. For example, take velocity. If I say a car is moving at a velocity of 50 meters per second, that's not enough information. Is it going east? Is it going west? And so on. So you need specified direction. Okay, so velocity is a vector because of that. If you take force, for example, another example, you can say the force is maybe 40 newtons. But which way is it pulling or pushing? Is it pushing east, west, and so on, or north? All right. So force is a vector quantity. Another quantity is acceleration. You would like to know which way an object is accelerating. Let's say the acceleration 2 meters per second square, but which way is it accelerating, and so on. Okay, so all these physical quantities are called vectors because they have directional properties. You need specified direction in addition to magnitude or a number and a unit. Okay, now let's look at graphical representation of vectors. Graphical representation of vectors. Graphically, vectors are represented by arrows. Okay, represented by arrows. So a vector has two properties. It has a property of magnitude and a property of direction. So if this arrow is to represent a vector, it has to represent both the magnitude and the direction. Obviously, the direction of the vector is represented by the direction of the arrow. The direction of the arrow. And the magnitude, or the numerical number of the vector, the magnitude, is represented by the length of the arrow. The length of the arrow. In other words, the length of the arrow is drawn in such a way that it's proportional to the magnitude of the vector. In other words, you need scale. You need a scale to represent it. Okay, so the length is drawn in such a way that's proportional to the magnitude of the vector. So that way, an arrow represents a vector graphically. Its length represents how big the vector is, and its direction, of course, represents the direction of the vector. Let's look at some examples. Suppose you have the following velocity vector. Let's say it is A equals maybe 40 meters per second, and let's say it is 30 degree maybe west of north. Okay, let's represent this vector graphically. First, we need a scale. This is velocity, but we're going to represent it by length. So again, we need a scale to relate the velocity with a length. Okay, so in this case it makes sense to make the representation let 10 meters per second be represented by 1 centimeter. So we're going to say let 10 meters per second be represented by 1 centimeter. Okay, so it follows that the length of this velocity vector would be 4 centimeters. All right, so it's going to be the length will be 4 centimeters. Now let's look at the direction. The direction is 30 degrees west of north. Now in the coordinate plane, this one is east, this is north, this is west, this is south. Okay, 30 degrees west of north means you start from north and then you go 30 degrees west. Okay, the reference line, this one is the north, and then you go 30 degrees west. So this is our north, so you measure 30 degrees, and remember, according to this scale, it's going to be 4 centimeters, so we measure 4 centimeters this way, and this is the representation of the vector. Okay, 30 degrees north, west of north. This angle is 30 degrees, and the 4 centimeters, according to the scale, represent as 40 meters per second. But sometimes, you know, in this case, we're told to measure the angle with respect to north, but most of the time I'll just give you an angle because there is a default line. The default line in physics is this line over here, east. So if they ask you the direction certain angle, you measure with respect to this line over here. If it is positive, you go this way, that is counterclockwise. If the angle is negative, you go this way, that's clockwise. Okay, so let's consider an example. Let's say A. Let's take example again, the velocity vector, meters per second at 120 degrees. Okay, what this means now is you start from this line from east, and this positive, you go counterclockwise 120 degrees. Okay, so let's see how to represent this. First, we're going to scale. Again, we're going to say let 10 meters per second be represented by 1 centimeter, so this will be represented by 3 centimeters. Now 120 degrees, if no reference line is given, the reference line is this line over here. In other words, the direction of this one is 0. So we have 90 degrees over here, we add another 30 degrees, so we get this vector over here. Okay, so you've got 3 units, which according to this scale means 30 meters per second, and then 120 degrees from this line, you see this one is 30 degrees over here. Okay, how about if the vector was, let's say, A equals let's say 20 meters per second at negative 45 degrees. Okay, so the negative means you have to go clockwise. Okay, so this vector, well, if you use the scale 10 meters per second for 1 centimeter, will be 2. And then no reference line is given. This is the default angle. We're going to measure from here, and this is negative. We're going to go clockwise. Okay, so we measure 45 degrees, and then we go 2 units in this direction. Okay, so this would be the angle. So this is the graphical representation of vectors. Now let's define what we mean by opposite of vector. Opposite of a vector is a vector with the same magnitude but opposite direction. This is a vector with the same magnitude but opposite direction. Opposite direction. Okay, for example, let's say vector A is 2 meters east, the negative A would be 2 meters west. Okay, so this vector is this one, while this vector is this one. Okay, you just reverse the direction, and the difference in the direction of the two vectors would be 180 degrees if you reverse it. Okay, now let's look at multiplying multiplying a vector by a number. Multiplying a vector by a number. Okay, multiplying a vector by a number simply multiplies the magnitude by the number. If the number is positive, the direction is the same, but if the number is negative, the direction becomes opposite. Okay, so the magnitude is multiplied by the number. The magnitude is multiplied by the number, and the direction remains same if number is positive. If the number is positive and becomes opposite if the number is negative. Okay, the number is negative. For example, let's say A is 2 meters north, okay, which is this vector over here. How about 2A? 2A would be simply this will be multiplied by 4 meters, and since this number is positive, it remains in the same direction, okay, north. So this vector would have 4 units, it will still be north. How about negative 2A? Negative 2A, the magnitude will be multiplied by 2, will still remain the same, but the direction will be opposite, okay, it will be south, and this vector will be this one over here. Now we're going to look at adding vectors graphically. Adding vectors graphically. First, let's look at the meaning of adding vectors. For example, let's take displacement vectors. Let's say you have this particle over here, you displace it this way, okay? And then again, you displace it this way, okay? Let's call this vector A, let's call this vector B. What we call the sum of these two vectors is the single vector that does the same thing. The single vector that does the same thing is the vector that takes this point to this directly, okay? So that's what you call the sum of two vectors. It is the single vector that does the same thing, okay? The effect of these two vectors is to displace this particle from here to here, and the single vector that does that is called the sum of the two vectors, sometimes called the resultant. Now, you see, to add vectors, all you have to do is you connect the vector's tail to head like this. You got head, and then you start the tail of the second vector from the head. Then the sum vector is a vector connecting the tail of the first vector to the head of the first vector. Okay, so to add vector A and B, or more vectors, okay, connect the vector's tail to head, connect the vector's tail to head, okay, then the sum vector is the vector connecting, or let's say the vector whose tail is the tail of the first vector, the tail of the first vector, and whose head is the head of the second vector. Okay, that's how whose head is the head of the second vector. Okay, that's how you add vectors. So to add vectors graphically, all you do is you connect the vectors tail to head, and then the sum vector is a vector connecting the tail of the first vector to the head of the last vector. But of course you have to do this to scale. Okay, this length has to be drawn to scale, and also this direction is also has to be done to scale. Okay, let's look at an example. Let's say we have the following vectors. A is 4 meters east, let's say. B is let's say 2 meters north, and let's say C is 5 meters west. Okay, so we want to add these three vectors graphically. Okay, first let's represent this vector separately. Okay, A is 4 meters east, so we're gonna have 1, 2, 3, 4 in this direction. B is 2 meters north, is this vector over here. C is 5 meters west. Okay, so we're gonna have 1, 2, 3, 4, 1, 2, 3, 4, 5 west. So the vectors. Okay, so let's start from A. A is 4 meters west. Okay, 1, 2, 3, 4. This is A. And then B is 2 meters north. So this is A, this is B. C is 5 meters, 1, 2, 3, 4, 5. Okay, this is C. Okay, so we've connected them tail to head. So the sum vector is the vector that connects this point to this point. Is the vector whose tail is the tail of the first vector and whose head is the head of the last vector. So this vector over here, is what you call the vector A plus B plus C. Okay, so to add vectors graphically, all you have to do is you connect the vectors tail to head, and the vector connecting the tail of the first vector to the head of the last vector is what you call the sum vector. Now let's look at subtraction. Graphical subtraction of vectors. Graphical subtraction of vectors. Now remember, subtraction is the addition of a negative. Okay, so if you got A minus B, we can write it as A plus the negative of B. Okay, so A minus B is the same thing as the sum of A and the negative of B. So first you find the negative of B, which is the opposite of B, and then you simply follow the rules of addition. Okay, for example, let's say we have the following vectors. Let's say A is 4 meters east, and let's say B is maybe 3 meters south, let's say. So I want to find A minus B. The question is find A minus B. Okay, so we're going to write A minus B as A plus the negative of B. Okay, and then we're going to find these vectors, and we're going to follow the rules of addition to do it. Okay, so A, graphical representation of A is this one. We've got 1, 2, 3, 4 east. B is 3 meters south. Okay, this is B, 1, 2, 3. But we need negative B. Okay, and negative would be the opposite of that. It will be 4 meters north. Okay, so this will be 1, 2. Anyway, 1, 2, 3, negative B. Okay, so to find A minus B, we're going to connect A and negative B tail to head. Okay, so we start with A. A is 4 units east, 1, 2, 3, 4, and then negative B is 3 units. Okay, this is A, this is negative B. Therefore, this vector over here is a minus b, or a plus negative b. This is a minus b, right? Next, we're going to look at the analytic addition of vectors, but before we do that, we need to discuss components, because we need components of vectors to do that. So let's define components of vectors. Components of vectors. Okay, give me any vector A like this. Okay, I can write it as a sum of horizontal vector and a vertical vector. I take the projection of this vector over here, let me call that AX, and then I take the projection of the y-axis, let me call that AY. Okay, you see? So any vector A can be written as the sum of a vector, which is a projection on the x-axis or the horizontal vector, and a vertical vector. We can do that for any vector. These two vectors are called the components of a vector, okay? They're called the x component or horizontal component. This is called the y component or the vertical component of the vector, okay? So now let's try to relate these components with the magnitude and direction, okay? Suppose, let's say we have this vector, its length is a and its direction is theta, okay? And of course this will be the horizontal component ax, this will be the vertical component ay, okay? So I want to express this x component in terms of magnitude and direction. So if I use the definition of cosine of theta is defined to be adjacent divided by hypotenuse, that is ax divided by a, okay? That gives me ax equals a times cosine of theta. And if I use the definition of sine theta, which is opposite side divided by the hypotenuse, I get ay divided by a, okay? And that implies ay equals a the sine of theta, okay? So these are the formulas that take you from the magnitude and direction of the vector to the x and y components of the vector, okay? But components could be positive or negative, okay? For example, if you've got this vector over here, you see its x component will be to the left, which will be negative, okay? In this case, ax will be less than 0. And of course, we have ay greater than 0. If you've got a vector like this, you see both the x will be negative and the y will be negative, okay? So if you use the acute angle, if you use this angle over here, the calculator will give you positive values for both of them, okay? So if you use this angle, you will get this as positive in your calculator, but then you have to change it to the right side yourself. But if you take your angle to be the default angle, the angle with respect to this line over here, if you use this angle instead of this angle, the calculator will always give you the right sign, okay? In this case, with respect to this one, your angle will be this one over here, okay? So if you use this angle instead of this angle, the calculator will always give you the right sign. So let me see over here, provided theta is the default angle, which means measured with respect to the positive x-axis, measured with respect to positive x-axis or east, okay? So if you use this angle, your calculator will always give you the right sign for the components, okay? Let's consider an example. Suppose, let's say we have the following vector. Let's say it's 5 meters, okay? Let's find the components. Now, obviously the magnitude is 5 meters, right? So you've got a equals 5 meters. How about the direction? The direction is east, and if east is the reference line, so the angle is 0 in this case. Okay, this is trivial. You don't have to do the calculations, you know, because we don't have vertical component, we have an x component. But to be technical about it, we can say ax equals 5 times cosine of 0, and that'll be 5, and ay will be 5 times the sine of 0, and that will be 0. Okay, so a horizontal line, the horizontal component itself, but the vertical component is 0. How about it was like this? Let's say it was like this. Let's say this is 5 meters. Okay, so once again, the magnitude is 5 meters, but the direction, you see, we measure from this line over here from east. So this is the direction from this line. So it's 180 degrees. Okay, so theta is 180 degrees for this one. Okay, you measure this way, so 180 degree. So we have ax equals 5 times cosine of 180, which is -5. Okay, this to the left can be negative, and ay would be 5 times the sine of 180, will still be 0. Okay, how about if you have this vector over here? Let's say it's 2 meters. Okay, well, the magnitude obviously is 2 meters. The direction, as measured from this line over here, is 90 degree. Okay, so theta equals 90 degree, and we get ax equals 2 times cosine of 90 degree equals 0, and ay equals 2 times the sine of 90 degree, which is 2. Okay, so in this case, this vector doesn't have an x component, it's just a vertical force, and the vertical component is simply the vector itself. How about if we have like this? Let's say it's 2 meters. Okay, so in this case, the direction, if you come in a counterclockwise direction, is 270, or if you come this way, it's -90. Okay, so you can say a is 2 meters, and the angle is -90 degrees. Okay, so I'll have ax equals 2 times cosine of -90, which is 0, but the y component is 2 times the sine of -90, so you get -2, right? So these are for components for vertical and horizontal vectors. Now let's consider an arbitrary vector. Suppose, let's say we have this vector over here. Let's say we have this vector. Let's say it is 10 meters long, and let's say this angle over here is 37 degrees. All right, so we want to find the components. All right, so the magnitude is obviously 10 meters. All right, how about the direction? If you get the right sign, you have to use angle measured with respect to this line. Okay, so our angle is going to be this one, the default angle. Okay, so we're going to say theta equals 180 plus this angle. Okay, 180 plus 37, which is 217 degrees. Okay, so if you use this angle, you'll get the right sign for both vectors. All right, so we have ax equals a times cosine of theta, which is 10 times cosine of 270 degrees. All right, this will give you 10 times negative about 0.8 over here will be -8. Okay, it's negative because the x component is to the left, and the y component would be 10 times the sine of 217. Okay, it's going to be, that also is going to be negative because this is going down. Okay, so you got, that will be times about -0.6, and that's about -6 meters. So the components of these vectors are both negatives. Okay, next let's see how we get components from magnitude and direction. This was how to get components from magnitude and direction. Now we're going to look at component magnitude and direction from components. Magnitude and direction from components. Now you might have noticed what we call magnitude and direction is basically the polar coordinates we talked about in chapter 1, and what we call x and y components are the Cartesian coordinates we talked about in chapter 1. Okay, so now suppose we know the components. Okay, suppose we know this components over here, ax and ay. The question is, how do you find the magnitude and the direction if you know the components? Okay, for magnitude we can just use Pythagorean theorem. Okay, we have a squared equals ax squared plus ay squared. Okay, so that gives us the magnitude equals square root of ax squared plus ay squared. Okay, so we can calculate magnitude using this formula if you know the components of the vector. Now let's look at the direction. Now you see the trigonometric function that relates this to is tangent. So we can say the tangent of theta is the vertical component divided by the horizontal component. Okay, and then of course we're looking for theta, we're going to use the inverse. So that gives us theta equals tan inverse of ay over ax. Okay, but we gotta be very careful with this function because the predicate of this function is pi, it's not 2 pi. So for example, let's consider the following. Let's take this point. Okay, let's say it's 3 over here, 4 over here, and then let's look the points on the opposite side. Okay, so this would be -3 and this would be -4. Okay, now for this angle, you see if you're looking for this angle, will be tan inverse of 4 over 3. Okay, which should be 53 degrees. How about for this angle? For this angle, you see the components are -4, -3. We'll get tan inverse of -4 over -3. But remember, negative and negative gives you positive, right? So this is still tan inverse of 4 over 3. So the calculator will still give you 3 degrees. Okay? The calculator doesn't know you're on this side. Alright? So if you're on this side, you have to do it yourself. We know this angle over here is this angle, which is 53 degree plus 180 degree. Okay, so if you know you're on this side, if your vector is on this side, that's to the left of this line, you have to add 180 degrees to what the calculator gives you. Okay, so we're going to have the following definition because of that. Theta equals, you take the calculator value at its face value if ax is positive. Ax positive means you're on this side. Ax negative means you're on this side. Okay, so if ax positive, you can take the value you get from the calculator as it is. But if x negative, you have to add 180 degrees. It will be tan inverse ay over ax plus 180 degrees if ax is less than 0. Okay, so if you know you're on this side, the calculator will not give you the right answer. You have to add 180 degrees to it. Okay, we have also another problem. If you've got a vertical force like this, okay, its x component is 0, but division by 0 is undefined. Okay, so if you have vertical vector like this, the calculator will give you an error. You have to do it. Okay, so if your y component is positive and x is 0, you know the angle is 90 degree. If your x component is 0 but you got a negative y over here, you know it's negative 90. Okay, so you can say this equals 90 degree if ax equals 0 and ay is greater than 0. It will be negative 90 degree if ax is 0 and ay is less than 0. So with these 4 branches, you can find the direction of any vector. Okay, if you're on this quadrant, you know both y and ax is 0, then no problem. The only problem is if x negative. If x negative, you have to add 180 degree, but you don't look at y, you look at the bottom number, the x component. All right, so this is the formula for calculating the direction of a vector from its component. Okay, now let's consider an example. Suppose we have the following vector. Let's say this is our vector, okay, and then the coordinate system. Let's say we're told this angle is, well, let's say we're told this is -4 and so of course +3, okay, and the goal is to calculate the direction for this angle theta. Of course the default direction will be this one over here, okay, and so we want to find this angle and how big the vector is. Okay, so what we have is ax is -4 and ay is 3. Okay, a is obtained from Pythagorean theorem. You've got ax squared plus ay squared, okay, that is square root of -4 squared plus 3 squared, that gives us 5. How about the direction? Now our x is negative, so you gotta use this formula over here. Okay, so we have theta equals tan inverse of 3 over -4 plus 180 degrees. Okay, from your calculator you'll find out that this is -37 degrees. -37 degrees, okay, and then we'll add 180 degrees to it, 180 degrees, so that turns out to be, I think, 153 degrees. Okay, all right, next we're going to look at algebraic or analytical addition of vectors. Analytical addition of vectors. That is, we're going to see how you can add vectors algebraically. Okay, we have already seen how to add them graphically, but now we're going to see how we can add them algebraically using components. All right, so let's start from the graphical addition of vectors. Suppose we have the following situation. Okay, suppose we have this vector A and then we have this vector B. Okay, so as we learned from graphical method, all you do is you connect them tail to head. Then the sum vector is a vector connecting the tail of the first vector to the head of the last vector. So this is A plus B. Okay, let's call it R, or the resultant. All right, now let's look at the x components, x and y components. For A, this is ax, this is ay. Okay, if you look at B, you see this is bx, and this one over here is by. Now if you look at the sum, you see the sum is from here to here. So you see this is ax, this is bx, and the sum goes all the way from here to here, which is rx. Okay, this is ay, this is by over here, the sum goes from here to here, this is ry. Okay, so you can easily see the x component of the sum is the sum of the x components of the two vectors, and the y component of the sum is simply the sum of the y component of y components of the vectors. Okay, so what we have is if r equals a plus b plus c and so on, if you have some more, then Rx is simply the sum of the x's and so on, and Ry is the sum of the y's, okay, plus cy and so on. All right, now once you have the x and y components, then you can easily calculate the magnitude and direction of the sum. Now you see, this is the sum vector, and this is ax plus bx, the x component of the sum, and the y component is ay plus by. So we're trying to find the magnitude of the sum vector and the direction of the sum vector. Okay, so for the magnitude we just use Pythagorean theorem. So we have r equals square root of ax plus bx squared, and then ay plus by squared. Okay, and for the direction will be tan inverse, okay, tan inverse of the y, ay plus by divided by ax plus bx. Of course, if this number is negative, you're going to add 180 degrees. Okay, so maybe I'll say over here plus 180 degrees if ax plus bx is less than 0. All right, so these are the formulas that help you to add vectors. All right, so let's consider an example. Now let's consider an example of adding vectors analytically. Let's consider the following two vectors. Vector A, let's say, is 10 meters at 37 degrees, and vector B, let's say, is 20 meters, let's say 53 degree west of north. Okay, so first we have to obtain the components of these vectors. Of course, we're trying to find a plus b. Find magnitude and direction of a plus b. Okay, so we're going to start by finding components. Okay, let's start vector A. Okay, so for vector A, obviously the magnitude is 10 meters, and the 37 degrees is the default angle. That's angle measured with respect to the positive x-axis. So theta A is 37 degrees. Okay, so this vector is something like this, 10 and 37. Okay, so AX is A times cosine of theta A, which is 10 times cosine of 37 degree. Cosine of 37 is approximately 0.8, so this would be 8. And AY would be A times the sine of theta, that is 10 times the sine of 37 degree. Sine of 37 degrees is approximately 0.6, so it will be about 6 meters. All right, next let's do vector B. Okay, vector B is given with respect to north, so we're going to have to find the default angle. But first, the magnitude is 20 meters. Now we need to find the default angle for this vector. Okay, it says 53 degrees west of north. This is north. You go 53 degrees in this direction. This is this vector, okay? But I need the default angle. The default angle is angle measured from here. So you see it's 90 degrees plus 53 degrees, all right? So you've got theta B equals 90 degrees plus 53, which is 143 degrees. Okay, so bx equals b times cosine of theta. So this gives us 20 times cosine of 143. Okay, cosine of 43 is going approximately negative 0.8. So this would be 20 times approximately negative 0.8. It is negative because you see this component is to the left. All right, and then by is b times the sine of theta. That will be 20 times the sine of 143 degrees. Okay, this is the vertical component. So this is approximately about 0.6, so it's going to be 12. All right, so we have the components. Next is to find the magnitude and the direction. So let's start with the magnitude. The magnitude, that's r. R is square root of ax plus bx squared, and then ay plus by squared. Okay, let's plug the numbers. So ax is right over here, it's 8, and bx is negative 16. So we have 8 minus 16 squared, and then the y's. And for the y's, we have ay, which is 6, we have by, which is 12. So that is 6 plus 12 squared. All right, so the magnitude would be the square root of 8 squared plus 18 squared, or that is. Now for the direction, theta equals tan inverse of ay plus by over ax plus bx. Okay, so remember, if this one turns out to be negative, we're going to add 180 degrees. All right, so it looks like ax plus bx is negative, so we're going to add 180 degrees. Okay, that is 8 minus 16 is negative, so it's going to be plus 180 degrees because this is going to be negative in this problem. All right, so you've got tan inverse of ay plus by, this is our ay plus by, 12, and then ax plus bx is this one, 8 plus negative 16, negative 6. Okay, now since this is negative, if the x component is negative or the bottom number is negative, you have to add 180 degrees. All right, so this is tan inverse of 18 divided by negative 8 plus 180 degrees. Okay, we can factor out the negative. It's going to be tan inverse, and then we can divide by 2. That's going to be 9 over 4 plus 180 degrees. So you read this from a calculator, and that would be the direction.